Alright, more practice. Given a string pref and a sequence of words, find the first one with pref as prefix. Here's an example. So we are working with the prefix do, do, and it asks us to find from this sequence of words which word starts with do first. So you can see that the answer is donkey, but given this sequence, we don't know at the start when we will stop, so it might be natural to use a while loop here. Let's implement find first with prefix. So you want to go through all the words in the sequence and return the first one that starts with our prefix. How do we do that? So you can pause the video here, try to implement before looking at the answer. Okay, did you pause? Let's try to implement. Find first with prefix. And the prefix and the words. For word and words. Let's assume that there's an answer here. Or if there's no answer, then our function will return none. How do we check if a string is a prefix of another string? There's a helper function we can use. If word that starts with ref, return the word. Okay, let's try that. Let's run this assertion. And if there are no errors, then our function is correct, at least for this assertion. Alright, it works. So you can learn about this from the documentation. Here's another solution that uses break. And okay, so we did not actually use a while loop there. I guess we can use a while loop. So here we can also use this demonstration that we can use breaks in for loops as well. So for word and words, if word that starts with pref, we stop the loop and then we return the word. This works because the variable word takes the values from words one at a time in sequence. And if we break the loop, then the last value that word is referring to would be the word where this was true. So we return the correct word if we do this. Here's an alternate solution. We just return the word immediately when we find it. Here's another alternate solution, this time with exceptions, in case we don't find a word that starts with pref. So we raise a value error, indicating to whoever used our function that we encountered an error. Here's another version that uses generators and next. So this is a generator expression. It will produce all words for all words in word for all word and words if word starts with prefix. And we call next on that generator, which gets the first element from this generator. And that's what we want to do, right? Get the first word that starts with pref. This will raise an exception also if this generator happens to have no elements to yield, and you get a stop at iteration exception. So you can modify the code here to handle stop iteration. Actually, let's do that. So how do we handle exceptions? We can try here. So if this piece of code has an exception, then specifically a stop iteration exception, then we erase value error or something. Okay, this is a generator version of the code. If we run this, it should still work. Okay, let's try something. Let's try X here. It should raise a value error. Alright. Okay, it works. Here's another exercise. Make a generator that enumerates substrings. We've seen several implementations of non-empty substrings before, so you can check previous lectures to see those implementations. So both imperative as well as declarative in comprehension form, in recursion form. Okay, so this is not a new problem for us, but this time I want to make it a generator. So you can pause the video here. You can either come up with getting all substrings from scratch by yourself, or you can refer to previous implementations in previous lectures. Okay, did you pause? Let's now move forward with the slides. Here's an example with wishful thinking. We assume we have this function. We get all the substrings starting from some index I for a given string. And we want to go through all possible starting indices. And for each substring that starts at index I, we yield that substring. So we still have to implement this, but this is what we are doing. For all possible starting positions, get all the substrings that start from that position and yield each substring. So how do we implement substrings starting from index I? We just need to do something like this. We get all the slices starting from index I. So I until len s. Why is it j plus 1 and not j? Because we are getting non-empty substring. So to avoid the empty string, j should be greater than I. I mean this part of the slice should be greater than I. It starts at I, so the lowest value here is I plus 1. Okay. So we have this. For each element from a generator, we yield that element. So this is a generator. Also, this also yields, so this is a generator as well. So this is a generator here. This function returns a generator, so this is a generator here. Yielding the results of a generator inside another generator is useful enough that there's a shortcut for this kind of pattern. We have the keyword yield from, separated by space. So this for loop and this yield from expression statement are equivalent. It will go through all the elements that we can get from the generator. So try to remember this when you encounter something like this. You just want to get if you want to yield everything from a generator, just type yield from and then the generator. New syntax, yay. Okay, here's another example. Okay, make a generator that returns the first n elements of another given generator. So here's an example usage. This one prints 3 substrings of ABCD. So we want to write the function take that gets the first k results from any generator. Okay, here's a sample implementation of that. Let's write that down. So since we know how many to take, we can use a for loop. So take the first n from a generator. So something like try in range n. You're gonna yield. So you want to call next on our generator n times, right? So this is also a generator as well. Okay, so this will work. Let's set up a generator that we can use. For example, this one. Let's use the substrings. And let's define yield substring starting from. Okay. Okay, so let's try to use this on I take the first 3 substrings from non-empty substrings of, let's say, I don't know, hello. Okay, and what do we get? So of course the ordering in which the substrings are given depends on the implementation of our non-empty substrings. So I think we'll be getting the substring starting from index 0 first. So okay, we got the first 3 substrings starting from index 0. Okay, this works. However, our code will fail if there are if you're asking for more substrings than what the generator can generate. So this is fine. But we wanted to take 10 out of this generator here. Then we get a stop iteration because how many substrings, non-empty substrings are there from the string? We have 1, 2, and 3. So we only had, we're trying to take 10, so it failed. So okay, so we need to fix that. So we need to detect if there are no more elements to take from the generator. So that's what happened. It crashes if there are too few elements from the generator. How to fix? We try to yield the next, and if we cannot, then we break out of the loop. Okay, so we still have a for loop. We know the maximum amount of, we want to take n, but if we cannot take n, then we stop early. So we try to yield the next one. If we encounter a stop iteration exception, we break the loop. Okay, this should now work properly. Okay, it does not crash anymore. Okay, here's another example. Our code now works for generators, but it does not work for normal sequences such as lists. We cannot call next on something that is not a generator. So if we try to do this, we want our take function to also be usable for sequences that are not generators. So we should get 31 and 41 from here. But this will not work right now because a list is not a generator, so we cannot use the next function on it. So it would be nice if we can handle sequences as well. So one easy way to do that would be convert the sequence to a generator. And we can do that using the iter function, right? So gen here the user could have given a sequence. Just make sure that it is a generator by calling iter on it. If it was already a generator, then this does not do anything. So this is safe. And our previous code will now work. So let's update our implementation. We update gen we force it to be a generator. So even if I put something here that is not a generator, it's A, B, C. It will create a generator out of the sequence and the code will run properly. Okay, even if we try to take more than the length of that sequence. Alright, so let's go through a few more examples. Try to predict the outputs of these code snippets. Okay, first one. Try to guess before running in the Python shell. Okay, did you pause? What's the output? You'll get Lloyd, Yor, Anya, and Bon, right? Okay. Okay. Next example. What is the output of this one? You can pause the video here before proceeding. Okay, did you pause? What's your guess? For name in foragers pass. So we're actually not doing anything to the name, but what happens here? Oh, all the print statements got executed, as you can see. Alright, one more example. You want to print name instead of pass. Okay, you can pause the video here again. Try to guess what will happen and then resume the video. Okay, did you pause? What's your guess? Let's see the result. So it prints yield. So it does this print and then we print the Lloyd name that got yielded and then so on and so forth. Okay. How about this one? Create a generator from the function. What is the output in the terminal? Okay, you can pause here again. Alright, did you pause before I run this? Nothing gets outputted. So this is the thing with generators is if the code in generators only gets executed once you get an element from it, okay. So next we'll try calling next one at a time here from this generator. So let's run the code, but let's move to interactive mode. Okay, I get the next value one at a time from res. Oh, I get two things on the screen. A gets printed, and then the value that was yielded from the generator is Lloyd. If I get next again, I get B gets printed, and then I get your. So looks like the generator is remembering where it last, what's the last command that it did, right? So Lloyd your, stop at, because it looks like it's stopping at the last yield that it did. So I'll next again, see Anya, debond, then if I try to next again here, E gets printed, but there's nothing to yield anymore, so we encounter an exception. But E still gets printed, so in the generator, it really does remember where it last stopped. Okay. So good thing with generators are they don't run unless absolutely necessary, as you've seen. If we create a generator, no code gets run until we get the next element from it. And it pauses execution. It remembers where it last finished. And it only runs more code once you need the next value from it. And it will stop execution again once it yields a value. This kind of behavior is called lazy evaluation. And everything else that we've done so far is called eager evaluation, the opposite of lazy. Okay, so lazy, isn't that a bad word? We don't want to be lazy, right? We want to be productive. Of course, that's a different context for meaning for the word. What can we do with lazy evaluation that we cannot do with eager evaluation? So what's the point? Here's an example. We start with this while loop, which is not a generator. So this function is not a generator. Count from, starting from some number, while true, print that number, and then add 1 to the number. Keep doing it. And this is a while true. If I run this code, if I even try to run this code, you can see that it does not end. So if I count from 1, I'll get, as you can guess, an infinite loop. Just keeps counting up. I need to stop this. Okay, so it's an infinite loop. So you can't code like this. However, if I yield instead of printing, okay, well, if I run this, nothing happens because we are just making a generator. And we can get the elements one at a time by using next. Does not fail because it does not need to run. It only runs when it needs to. But if we try to go through it using a for loop, then we run into the same problem. So go through all the elements of the generator, but inside the generator it's a while true, so it won't run out of elements, so we run into the same problem, infinite loop. But what's good about here is if we take a finite amount of elements from it, then we don't have a problem. Let's use the take that we wrote from before. Just taking 5 elements out of a potentially infinite number of elements. Then our code runs properly, no infinite loop. And in fact, if we do it twice, you can see that it remembers, no, sorry, it does not work. Let's say we save this generator. Okay. Then, so we take 5 from here, and then we take 5 from it again. Okay, why is it not working? Ah, sorry. G is count from. Okay. Sorry about that. There. So let's print something in the middle just to show that. Pause. Okay, as you can see, we try to take, so we save the generator from here. Okay. And then we try to take the first 5 elements from the generator. So we took 5 elements from the generator and printed them. So these are the first 5 elements. Took a pause, and then it's the same generator. We take 5 elements from it again, getting 5, 6, 7, 8, 9. So the generator remembers that already gave 0, 1, 2, 3, 4, and then the next values that it will give are 5, 6, 7, 8, 9. So this is an example of lazy evaluation. Even for a potentially infinite sequence, if we take a finite number of elements from it, then our program will still stop. The generator will only execute code when it needs to. Okay? And it doesn't go into an infinite loop. So we can actually define potentially infinite sequences using generators. And if we take a finite number of elements from it, then we can actually, it seems like we're actually working with infinite sequences. Wow. That's how you generate an infinite sequence in Python. Of course, it only makes sense to use it with lazy evaluation. Otherwise, you just run into infinite loops again. And we can create a generator for an infinite Fibonacci sequence. It will yield Fibonacci numbers one by one. Okay, let's try this code. Let's say we want to get the first 10 Fibonacci numbers. Oops. Okay. For F and Fn and take, let's take the first 30 Fibonacci numbers. Print Fn. And this will not run into an infinite loop because we are taking a finite amount of elements from the infinite Fibonacci sequence. Nice. Okay. This is the power of lazy evaluation. So you can keep asking for values from this generator and it will give you values as long as you don't ask for all its values, because if you do that, you'll run into an infinite loop because the sequence will not stop. So this is how you implement infinite sequences. Okay, for example, if we take the first 10, put it in a list, you get the following. So we could potentially build infinite sequences using this pattern, a while true, and then use generators to yield values one at a time. So be careful how you handle these generators that produce infinite sequences. Just don't try to take all of the elements. Here's an exercise. Make a generator that takes 2 generators and yields corresponding pairs. This can be tricky if the 2 generators don't have the same number of elements to yield. I guess you need to stop gracefully once one of the generators are empty. So before proceeding to the code, you can pause the video and try to implement this yourself. Okay, did you pause? Let's proceed. You wanna ignore unpaired elements. So if one generator runs out, then you should stop. Here's an example. So we have 2 sequences. You wanna force them to be generators. While true, try yielding the next element from sequence 1 and next element from sequence 2 and put them together as a pair. If we encounter a stop iteration, so we're trying this block. If we encounter a stop iteration, that means at least one of the generators ran out of things to give, then we stop the infinite loop. So this is one way to do that. Okay, I hope you understand what's happening. We need this to force the sequences to be generators, so we can use next on both of them. Okay, using pairs and count from, the count from that we wrote from before, that's an infinite sequence, this one. And using pairs, we can now implement enumerate from, like this. Yield from pairs, count from index sequence. So count from starts the count at index value, and then pairs up this infinite sequence of indices with a sequence of values. This also works even if the sequence is infinite, which is nice. Lazy evaluation. One more example. Create a generator that iterates through a sequence in reverse. Okay, if you think about it, to be able to iterate through a sequence in reverse, you kind of have to know what the last element is. So it seems impossible. Okay, if we try to do our usual idiom for reversing, this won't work, of course, because we are dealing with generators. It cannot be indexed. And yeah, we can't do this because potentially this sequence yeah, we can't do this. The sequence is potentially a generator. We need all the elements from a generator to be able to reverse it. And if this is an infinite sequence, then we don't know what we're doing. We cannot get the reverse that easily. Okay. So here's a sample implementation. Okay, so we definitely have to get all the elements. Assuming that the number of elements is finite, then there. Okay. For I in range. Go through in reverse. Sequence I for I in range. Reverse of the range. Okay. So this will work. Note that this is a generator expression, so this is still lazy. So this only works for actual sequences, not generators. We cannot get the length of a generator. Okay, so it's okay to be lazy in terms of lazy evaluation. Don't be lazy when practicing and solving problems. Okay, so the examples that we did are actually built into Python. The enumerate from is actually just the enumerate built-in function. The pairs function is zip, pairing up elements from two sequences together. The go through in reverse is just the reversed function. Count from is the count, but for count it's not initially available in Python. Once you open Python, you have to import from a module called itertools, and this is how you do it. From itertools, import count, which leads us to our next lesson, which are modules. So for modules, we have the import function. So some modules in Python are not included by default when you run Python initially. To be able to use these built-in pieces of code, you have to use the import statement. Usually when we need a specific something, a function or whatever from a module, we say from, then the module name, import, and then what we need from the module. This itertools here is still built in. Someone wrote this before, some of the Python developers. So if this module exists, you can look for available built-in modules in our documentation. So you can import what you need from those modules. Common modules are the math module for math functions like trigonometric functions, the logarithms, etc. etc. You can also import variables. So not just functions, but variables. In the math module, there is the pi constant, and there's the cosine function. So if you want to import multiple things, you just separate them with commas. Or you could just import the math module directly, and you can access its contents using the dot operator. You would need to check the documentation to see what is available in each built-in module. Convention with regards to modules: names starting with underscore are considered private. Don't import those. Although you can import them, don't import them by convention. Also, another convention: put all import lines at the top of the program. So import everything you need at the start of your program. So usual code looks like this, especially with large projects. In the project, you can also do something like this. You can also import from your own files if they are in the same directory. Here's an example. If you have a utils.py file containing this, actually let's try that. Containing what? Find first with prefix, right? Find first with prefix. Oh, it's no longer here. Okay, let's save it. Okay, I'll save this. Utils.py. Okay, so I have this utils.py in the same directory as lecture16.py. Let's start from utils, import, find first with prefix. And then let's call that function. Print, find first with prefix, h, and then let's give it a bunch of apple, banana, hello, help. So if we run this, we should get hello, right? And we imported the function from another file that we wrote. Let's try that. Alright, we are now able to import functions from other files, which is nice if you want to separate functions according to their usage. You can write them in different files and just import across different files. So you can organize your larger projects this way by bunching together different functions in separate files. Okay. Nice. It's useful for organization purposes. In the project, definitely do this if you can. Especially for unit tests, just put them in a separate file so you can import them. And that's it. Sometimes in the lab, some problems you are allowed to import some specific modules. So be on the lookout for these. Most likely they will help you solve the problems vastly easily, quickly as well. And that's the end of this lecture. Please keep practicing and try to practice while loops and generators and lazy evaluation as well. That's it for lecture 16. See you in the next one. Goodbye.